Hello everyone, today we will start with session 5 of coordination compounds. Students are requested to drop down their names for attendance purpose. We will be starting in a while. Okay, so everyone is there. Previously, I gave you some homework regarding the VBT theory, right? I gave you some complexes to find out their hybridization as well as to find out that there are outer orbital complexes or inner orbital complexes. Okay. So VBT theory, first we will explain according to the magnetic properties. Here, if you will see the hybridization, we will see the hybridization on the basis of configuration, and we will find out whether the availability of two vacant d orbital is there in n-1 level or not. Right, so we have studied that in octahedral complexes you may find two types of hybridization, that is D2sp3 and sp3d2, right? So D2sp3 will be when inner d orbitals are used and sp3d2 will be when outer d orbitals are used. This much we have covered in the previous session. Now titanium 3 plus, if you take, it has D1 configuration, right? So if it is having D1 configuration, let us draw the D1 configuration. One electron here, right? Now for the D2sp3 hybridization, two d orbitals are vacant here, right? So it can show D2sp3 hybridization. Similarly for vanadium 3 plus, vanadium is what? 4s2 3d2, right? So vanadium 3 plus will be equal to, vanadium is, cadmium, titanium, vanadium 4s2 3d3, right? So vanadium 3 plus will be 2 electron will go from here and 1 electron from here, so you will have D2 configuration. Now again, if you will have D2 configuration, you are having two vacant d orbitals which can contribute to D2sp3 hybridization. So in this also D2sp3 hybridization is possible. Now you come on to chromium 3 plus. So chromium is what? 4s1 3d5. So 3 plus will be equal to what? D3. Right, again you will do D3, two orbitals are vacant and it will show D2sp3 hybridization. Right, now here comes chromium 2 plus, manganese 2 plus, Fe2 plus and manganese 3 plus, Fe3 plus and cobalt 3 plus. So if you look at chromium 2 plus and manganese 3 plus, they are having D4 electronic configuration. Right, now one electron will be present here. So availability of two vacant d orbitals in n-1 will not be there. Right, either you should have a strong field ligand to pair up these electrons, otherwise they will show the sp3d2 hybridization. Similarly in case of d5 and d6 also, as there are no vacant d orbitals in n-1 level, so their hybridization will depend upon the type of ligand that you are using, right? So if the ligand will be able to pair up the electrons, then it can have D2sp3 hybridization, and if the ligand will not be able to pair up electron, that means it is a weak field ligand, then it will show sp3d2 hybridization, that means it will use the outer d orbitals. Okay, this much should be clear to all. Yeah. So basically D2 in these configurations, D2sp3 or sp3d2 will depend upon the type of ligand that you are using. If it is a strong field ligand, then pairing of electron would take place and it will show D2sp3 hybridization, and if there is a weak field ligand, then only sp3d2 hybridization is possible, in which the d orbital will be used from the outermost shell, right, not the n-1 level. Now this all I gave you as homework, you can match your answers here. So this is manganese cyanide 6 3 minus. So if you find out the electronic configuration, so first you find out the oxidation state, so this will be x minus 6 equals to minus 3. So manganese would be in +3 oxidation state, right? So now write down the electronic configuration for manganese. So for manganese it is 4s2 3d5, right? So 3 plus will be equal to what? D4, right? Now D4 will be somewhat like this: 1 2 3 4 5. So 1 2 3 4. As cyanide is a strong field ligand, so pairing of electrons will take place. This electron will go here, this electron will go here, right? So this resulting configuration will be obtained. 2d orbitals are vacant of inner shell, that is the n-1 shell. That is why we are obtaining the D2sp3 hybridization, right? Again here if you see, manganese is in +3 oxidation state, but here what is happening, because Cl is a weak field ligand, so it will not be able to pair up the electrons. So instead of using the 3d, we will use the 4d orbital, and it will show the hybridization as sp3d2 hybridization, because 3d orbital will not be involved in hybridization, rather 4d orbital will be involved. Okay. So this is the outer orbital complex and this one is the inner orbital complex. The cyanide one is the inner orbital and Cl1 is the outer orbital complex. Next is FeCN6. Again Fe is present in +3 oxidation state. Here also Fe is present in +3 oxidation state, but the difference is that here the ligand is strong field ligand and here the ligand is weak field ligand, right? So here, because it is a strong field ligand, it will be able to pair up electron. Fe3 plus is what? Fe is 4s2 3d6, so it will become what? D5, right? Now D5 pairing of electron will take place and it will become like this. 2 vacant d orbitals will be there, so it will show D2sp3 hybridization. But as fluorine is a weak field ligand, therefore it will not be able to pair up the electrons. Therefore 3d orbital will not be used for hybridization, rather 4d orbital will be used for the hybridization. Therefore it will show sp3d2 and it is a outer orbital complex, and this one will be the inner orbital complex. So by looking at the ligand you can just decide. Okay. Next you come on to cobalt C2O4 3 minus, so this will be cobalt 3 plus. Here also cobalt 3 plus. I told you already that cobalt 3 plus with oxygen donor, if there is a ligand which is donating from oxygen, right? For example H2O or oxalate ion you can also take. So for cobalt 3 plus the oxygen donors behave as a strong field ligand. So here you can see that cobalt 3 plus will be, cobalt is 4s2 3d7, right? So cobalt 3 plus will be what? D6. Now as oxalate will act as a strong field ligand, therefore it will pair up electrons. 2d orbitals will be vacant, therefore it will show D2sp3 hybridization by using the 3d orbital. Here if you will see that fluorine is a weak field ligand, right? So it will not be able to pair up the electrons. This is the D6 configuration. It will not be able to pair up the electron, it will use the 4d orbital rather, and therefore it will show sp3d2 hybridization. Is it clear to all? Is someone facing some sort of problem regarding these complexes, or you are able to understand that which one will be classified as inner orbital complex and which will be classified as outer orbital complex, and which one will be D2sp3 and which one will be sp3d2? Is it clear to all? Let me know in the comment section box. Are you able to classify the complexes as strong as D2sp3 or sp3d2, or inner or outer orbital complexes? Is the valence bond theory clear to all? It is very important from the examination point of view. You can let me know in the comment section box. Either give a thumbs up or drop a letter Y indicating that yes, you have understood. Okay, good. Now next is, see, while the valence bond theory explains the formation, structure and magnetic behavior of coordination compounds, it has some drawbacks, right? So what are the drawbacks? First, it does not give quantitative interpretation of the magnetic data. It only tells that the substance is paramagnetic or diamagnetic. It does not relate to magnetic susceptibility, right? And it does not explain the color that is exhibited by coordination compound. It does not give a quantitative interpretation that whether a complex is thermodynamically stable or kinetically stable, right? So I guess we have done in the session 1 that what are labile complexes and what are inert complexes. That is also not explained by the valence bond theory, right? That which will be thermodynamically stable or kinetically stable. So these all things are not explained by valence bond theory. Now, it does not make exact predictions regarding the tetrahedral and the square planar structure, right? It just explains the observation that this will be tetrahedral or this will be the square planar. But as we have seen in some compounds, for example, 4s2 3d8 in nickel, right, becomes 3d10, or we have done the example of copper, ammonia, 4. This complex, I guess we have done, right? In this complex, it is following a dsp2 hybridization. Rather, we were predicting that it should follow sp3 hybridization, right? So it does not clearly make the exact prediction that which complex will be tetrahedral or square planar, in which particularly the coordination number comes out to be 4. Right? It has just explained the observation because the structure of copper complex was found out to be square planar. So it explained that one electron will be shifted to the p orbital. Otherwise, according to valence bond theory, the structure should be of sp3 hybridization, right? But it is of actually dsp2 hybridization. So this is one important drawback of valence bond theory. Now, it does not distinguish between weak and strong field ligands, right? It is discussed by crystal field theory rather, which we will be doing in today's class. Now, you let me know the answers for the questions. What are the types of hybridization involved in the following geometrical shapes of the complex? You have to tell me the hybridization. What should be the hybridization? For square planar, what is the hybridization? For tetrahedral, what is the hybridization? And for octahedral, what is the hybridization? This is a very easy question. You just have to tell me the hybridization. Which square planar complexes, tetrahedral or octahedral complexes follow? Anyone with the answer? Anyone with the answer? What types of hybridization? For each, you have to tell me the hybridization. That means for square planar, what hybridization is there? Tetrahedral, what hybridization is there? And octahedral, what hybridization is there? For example, in valence bond theory, in chemical bonding that we study, in which covalent bonds are formed, we say that trigonal planar is having sp2 hybridization, right? Similarly, here also you have to tell that square planar will follow which hybridization, tetrahedral will follow which hybridization, and octahedral will follow which hybridization. Okay, so Sham and Siddharth have given the answers. Square planar is dsp2, tetrahedral will be sp3, and octahedral will be d2sp3 or sp3d2. Yes, you are correct with your answers. Good. Right? So we have already learned sp3 is tetrahedral, dsp2 is square planar, sp3d will be trigonal bipyramidal, sp3d2 and d2sp3 will be octahedral depending upon the type of complex that is being formed. If it is inner orbital, then we will use d2sp3. If it is outer orbital, then it is sp3d2. Good. Now the next question is, yes, Siya Lakshmi, you are also correct with your answer. Good. Next is Arun, you are also correct with your answer. Now for question number 2, you have to tell me that which of the following statements about the complex COF6, where CO is cobalt, right? It is a metal, it is not carbonate. Cobalt F6 3 minus, which is paramagnetic in nature, is correct. It is already saying that it is paramagnetic in nature. So you have to tell that amongst A, B, C and D, which statements are true about this particular complex. Fluorine is a weak field ligand. This is a prior knowledge that you should have for this question. Fluorine is a weak field ligand. And here the oxidation state of cobalt will come out to be what? Find out the oxidation state of cobalt. Then consider that fluorine is a weak field ligand. Then you have to tell the hybridization. You have to tell that which oxidation state is followed by fluorine and cobalt. Sham and Siddharth are saying B. Okay. Yeah, so the answer is B. Good. You both are correct with your answers. See what is happening here, that cobalt is in +3 oxidation state. So X minus 6 equals to -3. That means fluorine is in -1 oxidation state and cobalt will be equal to -3 plus 6. That will be coming out to be +3 oxidation state. Right? So this statement is incorrect. This statement is also incorrect. Now you have to find out the hybridization that is followed by this complex. So as we know that fluorine is a weak field ligand, right? So cobalt, the electronic configuration will come out to be 4s2 3d7. Cobalt 3 plus will have d6, right? So this is the electronic configuration, that is d6, right? Now because fluorine is a weak field ligand, it is not able to pair up the electrons of 3d. So we will use 4d for hybridization. And therefore, the hybridization will come out to be sp3d2 hybridization. It is the outer orbital complex. So, you both are correct with your answers. Good. Yeah, sp3d2 hybridization. Yes, Arun, Siya Lakshmi, you are also correct with your answers. Now, give the answer for this third question. Question number 3. These are the 3 complexes. You have to tell that which of them are paramagnetic and which of them are diamagnetic amongst A, B, C, D. Work out the hybridizations and you need to find out the number of unpaired electrons also in these 3 complexes and then decide that which one is diamagnetic and which one is paramagnetic. In nickel carbonyl 4 complex, basically the tetra carbonyl complex of nickel, you will have oxidation state of nickel as 0. Here you will have oxidation of nickel as +2, and here also you will have +2. Remember that the coordination number is 4 in each case. So two type of hybridizations can take place in coordination number 4, that is DsP2 or sp3. Work out and let me know the answer. Okay, Sham and Siddharth are saying, Siddharth is saying option C. Okay, and Sham is saying that nickel cyanide 4 is diamagnetic. Okay. Okay, so let's find out. See, if you will find out for this complex, that is the cyanide complex of nickel, it is square planar, it is having DsP2 hybridization. Already we have explained the hybridization in the previous lecture, right? I hope you remember it. So it is square planar and it is diamagnetic, right? Whereas if you will consider this, the chloride one, it is tetrahedral and paramagnetic. And here if you will see, it is diamagnetic and it is an outer orbital complex. So it will have sp3 hybridization. Remember that 4s2 3d8 was converted into 3d10 4s0 and then sp3 hybridization was taking place, right? So here D is also fully filled, S is also fully filled and 3 P's are also fully filled. So therefore it is a diamagnetic. So the answer will come out to be C. Yes, you people are very much correct with your answers. Good. Next, all the octahedral complexes of nickel 2 plus must be outer orbital complexes. Why? Give answer for this. Yes, Sham and Siddharth, you are correct for the previous answers. For the previous question. Now explain this question. Question number 4, I guess it is. So all the octahedral complexes of nickel 2 plus must be outer orbital complexes. Justify this statement. Why? Nickel 2 plus is what? Nickel is 4s2 3d8 and nickel 2 plus will be 3d8. Now tell me that why all the octahedral complexes of nickel 2 plus must be outer orbital complexes. Yes, C.R. Lakshmi, you are also correct for the previous question. So D8, if you will see, this will be somewhat like this. 1, 2, 3, 4, 5 and then 6, 7, 8. What is there in D8 configuration that inner orbital complex cannot be formed? See, even if there is a strong field ligand, let us say that nickel 2 plus is having a strong field ligand, even if the electron pairs up, right, we are only having one d orbital. We are only having one d orbital. Okay, let me read your answers. Yes, very good, Siddharth and Sham. You both are correct with your answers. So here if you see that even if there is a strong field ligand, pairing of electron will take place, only one d orbital will be vacant, right? And in case of octahedral complexes, we require 2d orbital as vacant. So instead of using the inner d orbital, only the outer orbital will be used, even in the case of strong field ligand, right? So the hybridization will always be sp3d2 for nickel 2 plus complexes, irrespective of the type of ligand that is present. Good. So here you can see this already have explained, okay, that d2sp3 is not possible because only one d orbital will be vacant here, okay. Now this question is the last question for VBT, I guess. A magnetic moment of 1.73 Bohr magneton will be shown by one among the following compounds. You have to tell me that which complex will have a magnetic moment of 1.73. Already I have told you that one unpaired electron will give you 1.73, two unpaired electron will give you 2.8, then 3 unpaired electron will give you 3.9, then 4, 4.9, 5 and approximately equal to 5.9. This is a shortcut, right, that you can follow. These are the number of unpaired electrons and these are their magnetic moment. Now you tell me which amongst the following compounds or which amongst the following coordination complexes you will have a magnetic moment of 1.73 Bohr magneton. Okay. Yes, Siddharth, you are very much correct with the answer because we have discussed in previous class also that copper NH3 2 plus will be having a 1.73 Bohr magneton. Yeah, Sham, you are also correct with the answer. Good. So C is the option here, right? We have already discussed this in previous class. I'll explain you once again. So here if you will see that copper is what? 4s2 3d9. Or you can also say that 4s1 3d10 to be more appropriate because of the anomalous configuration that it follows. So copper 2 plus will be equal to d9, right? And what will happen here, that the one electron will move to the p orbital, right? And it will follow dsp2 hybridization. So except this one electron, all electrons are paired. So this, because of this one unpaired electron, we will have a magnetic moment of 1.73 Bohr magneton. And rest of the complexes will have a different magnetic moment. Now one more question, you can take it for homework, that you have to find out that what is the magnetic moment for rest of the complexes. That means A, B and D, you have to find out that what are the magnetic moments here. Okay. Yes, Arun, you are also correct with the answer. Good. Now see, we have done two theories of coordination compounds, two major theories, that is the Warner's theory and the valence bond theory, right? The third theory and the last theory that is in our syllabus is crystal field theory, right? Other theories are also there, ligand field theory and molecular orbital theory, but these are for higher classes. We have to study crystal field theory. So here what is happening here, that crystal field theory considers that there is only ionic interaction between the metal and the ligand, right? Between the metal and ligand only ionic interaction is taking place. Basically it is neglecting the covalent character here, right? It is saying that the ligand and the metal is having only ionic interaction. It says that ligands are treated as point charges in case of anions. For example, if you are having F minus, Cl minus, O2 minus, these ligands are considered as point charges, right? And in case of neutral molecules, for example, CO, H2O, NH3, these are treated as dipoles, right? So here you can treat it as a dipole because it will have a dipole moment like this, because oxygen's electronegativity is greater than that of carbon. Here also a dipole will be there, as water is a polar molecule, and ammonia will also have a dipole moment because it is also a polar molecule, right? So anions will be considered as point charges and neutral molecules will be considered as dipoles. So it is saying that, let us say that metal is present here, right, and the ligand is of negative charge, point charge basically. So it is having a ionic interaction. That means electrostatic force of attraction is taking place between the ligand and the metal, right? Now the 5d orbitals of the metal in its gaseous state, or basically you can have a metal ion also if it is charged, right? So they will have the same energy. That means the 5d orbitals will remain degenerate in case of an isolated gaseous metal atom or gaseous metal ion, right? But as soon as the ligand approaches the metal, what happens that the d orbitals have a split in their energy. For example, let us say that I am taking metal atom, right, or I am taking a metal ion. Now it will have d orbitals of equal energy, 1, 2, 3, 4, 5. These are of equal energy. Now as soon as the ligand approaches the metal, what happens here that the degeneracy of these 5d orbitals break out, right? That means it is splitting into two sets. I will explain this in next slide. See here, the d orbitals, due to the approach of the ligand, or you can tell basically because of the electrostatic interaction that is taking place between the metal and ligand. When the ligand is approaching the metal, the d orbital splits into two parts, right? Without ligand, they all will be degenerate. That means all d orbitals will have same energy. But when ligand will approach with metal, will approach the metal, not with metal, when the ligands will approach the metal, the d orbital will be split into two parts, that is the T2g orbitals and the Eg orbitals. In two sets they will be broken down, right? So dxy, dxz and dyz will have a similar energy, while dx square y square and dz square will form Eg orbitals. So two set of orbitals we are obtaining. I'll show you how this works. For example, let us say we are having this d orbital 1, 2, 3, 4, 5. Right? These are 5d orbitals which are degenerate in energy. Now the ligand has not approached yet. When the ligand has approached here, what happens here that these d orbital splits into two sets. Splits into two sets. Now it can be either ways, either the Eg can be above or the T2g can be below, or you can have the reverse also, that T2g can be above and Eg can be below, depending upon the type of complex that is being formed, that we will be discussing in the next slides, right? So for meanwhile you can take that the d orbitals, 5d orbitals split into two different energy orbitals. So one is known as T2g, in which one will be dxy, dxz and dyz, and the other set of orbitals will be Eg, in which one will be dx square y square and the other will be dz square. Okay, so this you have to remember. Now crystal field splitting in octahedral coordination entities. So first we will study for octahedral complexes in which the coordination number of metal atom comes out to be 6. Right. So what is happening here? See, this you need to remember, that metal is having d orbitals, right? 5d orbitals it is having. Now if there is a direct interaction between the ligand and a d orbital, more of the repulsion will take place, because ligand is also electron rich and d orbitals will also have electrons. So electron-electron repulsion will take place, and where the electron-electron repulsion will take place, that means what? That energy will be raised up, energy will be greater. So if you are having a direct interaction of d orbital and ligand, what will happen? That particular d orbital will be higher in energy because of electron-electron repulsions. Electron-electron repulsion between whom? Between the electrons of the ligand and the electrons present in the d orbit. Okay. So here if you see in octahedral complexes, The coordination number is 6. So somewhat like this. Right? And so the ligand will approach in these directions. Let us say that the ligand will be approaching in these direction. So clearly you can see that dz square will be lying here, plus, minus, right? And dx square y square will be lying here. So dz square and dx square y square are having a direct overlap or a direct interaction from the ligands. Right? Therefore, the repulsion will be raised for dx square y square and dz square orbital. And these set of orbitals, that is dx square y square and dz square orbital, are known as Eg orbitals. That means the Eg set of orbital will be higher in energy as it is facing more repulsion due to the direct interaction between the ligand and the orbital that is comprising the Eg set. Okay, while if you will see dxy, dyz and dxz, there is no direct interaction between the ligand and these T2G set of orbitals. Therefore, they will be in lower energy than that of the Eg set. Right. So, this much you have to take in consideration, that for octahedral complexes, because dx square, y square and dz square orbitals are facing direct interaction from the ligand, so they will be higher in energy, while T2G orbitals will be lower in energy. So T2G will be below and Eg will be high. Eg will be high because this is the graph for energy, that the energy is increasing upwards. So Eg will have a greater energy than that of T2G. Okay, so here you can see these are the metal d orbitals, right? When the crystal field basically is spherical, the energy of d orbitals raise up and then they finally split into two set of orbitals, that is Eg and T2G. In octahedral complexes, Eg will come upwards and T2G will come downwards. And the separation between Eg and T2G is known as crystal field splitting. It is known as crystal field splitting and it is represented by delta O. O stands for octahedral. Delta stands for energy difference between the two. Right? So, crystal field splitting is known as delta O. Now, this is the barycenter. This is the barycenter, right? From here to Eg, the distance will be 3 by 5 delta O. Not the distance, rather the energy difference will be 3 by 5 delta O. And this much energy corresponds to 2 by 5 delta O. These are very important. You have to remember this by heart. Again, I'll repeat that on approach of the ligands, Eg set of orbitals will face much more interaction, much more repulsion than that of T2G. Therefore, Eg raises in energy and T2G lowers in energy, right? The energy difference between the Eg and T2G is known as crystal field splitting because we are studying octahedral complexes. Therefore, we write it as delta O. Delta O means the energy gap between the Eg and T2G. Now, this is the barycenter. If you take this barycenter, here if you will take that, the energy difference between the barycenter and Eg is 3 by 5 delta O, while the energy difference between barycenter and T2G is 2 by 5 delta O. Okay, where O stands for octahedral complex. I hope this is clear. Now next, we will study about the factors which will be affecting crystal field splitting, that is delta O. Okay, so this all I have explained, that Eg energy will increase by 3 by 5 delta O and T2G will decrease by 2 by 5 delta O, where delta O is the crystal field splitting and O stands for octahedral complexes. Now, the factors on which delta O depends. First one is the field that is produced by the ligand, right? We are having two types of ligand. We are having strong field ligand and we are having weak field ligand, right? So, strong field ligand have much more interaction with the metal, and what happens here is that delta O is very large. The splitting is very large, right? That means the energy difference between Eg and T2G will be much higher in case of strong field ligand. While in case of weak field ligand, if you will see that delta O will be less, because they will not be able to interact much with the metal. Therefore, the delta O will be less in case of a weak field ligand than that of a strong field ligand. So, this is the first factor, that is the type of ligand. Now, the strength of ligands, this all we have discussed, that according to spectrochemical series, they are arranged. So, you can remember this, that I minus, Br minus, all the halogens if you will take, they are weak field ligand, right? And Cn minus, ethylene diamine and carbonyl, they are strong field ligands. For NH3, we have discussed the case, that what is the case for NH3 in 2+, it behaves as weak field ligand. In 3+, it behaves as strong field ligand in case of octahedral complexes, while in case of tetrahedral complexes, the metal can be of any oxidation state, it will behave as weak field ligand only. Okay. Now, the second factor on which it depends is the charge or oxidation state of metal. That means, let us say you are having two metals, M3 plus and M2 plus, right? So, the one which will have a greater oxidation state will have a larger delta O. That means it will have a larger energy separation between Eg and T2G. So, the higher the charge on the metal atom, higher is the splitting of the energy levels, because what will happen, see, higher charge means what, that it will attract the ligand toward itself more, right, because it is much electron deficient. So, as the positive charge on the metal increases, what happens, that the ligand metal interaction increases and therefore the repulsion also increases. You can remember that more the attraction between metal and ligand, more is the repulsion between d orbital and ligand, and therefore the delta O will increase. More repulsion means that delta O will also increase. Greater is the crystal field splitting. Remember this, more the attraction between metal and ligand, more is the repulsion between d orbitals and ligand, and therefore the delta O will also increase. That means the crystal field splitting also increases. So here you can see, if you increase the positive charge on the metal atom, the ligand will be more attracted towards the metal atom than that of M2 plus. M3 plus will be more able to attract the ligand towards itself. More it will attract, the more is the repulsion between the d orbital of this metal atom and the ligand, and therefore the delta O will also increase. In short, you can remember, higher the oxidation state of metal atom, higher will be delta O. Now next is the row of the metal in the periodic table. So see, we are considering here basically D block elements, right? So we are having 3D, 4D, 5D series, 6D series is incomplete, and basically we don't have much importance of 6D series. So we considered only 3D, 4D, 5D here, right? So 3D and 4D and 5D and 6D are the four transition series of D block. Now, for and 5D, the delta O will always be higher. The delta O will always be higher. Right, than that of 3D. So, down the group, what happens? That delta O increases if the ligand and the oxidation states are same. Right, you have to remember the if clause, that the ligand and the oxidation state has to be the same. Then you can compare that 3D, 4D and 5D series amongst them, which metal atom you are having, right? So here if you see ruthenium and iron, right? So delta O will be greater for ruthenium than that of iron. They are having the same oxidation state and also they are having the same ligand, right? Next, so now we will study about the electronic arrangement in octahedral complexes for central metal or ion. Now let us say that the number of d electrons is 1, right? So we are having T2G here, let us say, and we are having Eg here. T2G will be 3 orbitals, Eg will be 2 orbitals. So D1, 1 electron will be here, so the electronic configuration will be T2G1. 2 electrons is there, so this will be T2G2, right? Hund's rule is being followed, right? So T2G2. Then you are having T2G3. So T2G3, it will become half it and it is also stable. Now when you come to T2G4, basically when you add the fourth electron, not T2G4, but when you add 4 electrons, number of d electrons is 4. Now you are having two possibilities, right? Either you put the fourth electron here or you put the fourth electron in the Eg orbital, right? So two possibilities are there. Till 3, T2G will be occupied. For the D4 arrangement, two possible arrangements are possible, that either the electron goes into the T2G level, right? That means it will be somewhat like this, 1, 2, 3, here you are having 2. So the fourth electron will be going here, or you can have another option that it goes in the Eg orbital, 1, 2, 3 and then Eg you are having 1, right? So here what is happening, that the pairing of electron is taking place first, and here what is happening, that pairing of electron is not taking place. So you can remember this, that delta O is the crystal field splitting, and P can be represented as pairing energy. That means the energy which is required to pair up an electron is known as the pairing energy. Right. Now these two factors will decide that whether your electron will go into T2G, the fourth electron, or the fourth electron will go into Eg orbital. So let us see here that if delta O is less than that of pairing energy, that means what? That pairing energy is greater than that of the crystal field splitting. That means it is harder to pair up an electron. Then what will happen? That Eg orbital will be having that electron. Pairing energy is more, means what? That it is harder to pair up electrons. So we will not pair up the electron. We will move the fourth electron to Eg orbital, right? So this becomes T2G3 Eg1. And the ligands for which this condition takes place, that is the pairing energy is greater than that of delta O, are called as weak field ligands. So this is the description of weak field ligand and strong field ligand, which was not explained by valence bond theory, right? So it was explained by crystal field theory rather, that weak field ligands are those ligands in which the pairing does not take place because the pairing energy is higher than that of the delta O or the crystal field splitting in octahedral complexes. Right, therefore they form high spin complex. Why they are known as high spin complex? Because the fourth electron, you can see that after T2G, Eg is being filled, right? We are not pairing T2G here, rather we are moving the electron to the higher energy level, that is Eg. That is why they are known as high spin complexes. While the other cases of strong field ligand, so in strong field ligand what happens, that crystal field splitting is greater than that of the pairing energy. That means the energy required to pair up an electron is less. So therefore what will happen, that pairing of electron will take place now. So here if you will see that the fourth electron will be occupying the T2G level. So this will become 1, 2, 3, 4 and no electron in Eg. So this will be T2G4 Eg0. These ligands are known as strong field ligands, and these complexes form low spin complexes. These complexes are known as low spin complexes in which the T2G is completely filled first and then you will fill Eg, that is known as low spin complexes. Is it clear to all? Is this clear to all? Let me know in the comment section. This is a very important aspect of crystal field theory. Basically, you can say that it is the gist of crystal field theory. So that is why I am emphasizing on it. You can let me know in the comment section box if it is clear or I need to explain it again. Let me know in the comment section fast. Okay, good. Next. Now, crystal field splitting in tetrahedral coordination entities. So, tetrahedral, you can imagine that a cube is there, right? And the alternate corners are occupied. So, this is the ligand, this is the ligand, this is the ligand, this is the ligand, and this will be the metal, right? So, here you can see that these ligands are arranged in tetrahedral manner. Now, dx square y square if you take and dz square if you take, they are not interacting directly with the ligand. You can see here that there is no direct interaction, right? You can compare the positions of the ligand and the d orbitals that you are making here. So, dx square y square and dz square if you are taking, they don't have direct interaction with the ligand. But in case of dxy, dyz and dxz, you can see that the ligand and the d orbital interaction is greater. So, now what will happen that T2 and E. Remember that for tetrahedral entities, we do not use G word. We do not write them as T2G or EG, rather we simply use T2 and E. Right? The reason basically is there in the higher classes. You don't need to focus upon this reason. Just you need to remember that G stands for Jared. G stands for Jared, right? So, G is not used in case of tetrahedral complexes. You will simply use T2 and E. So, you can see here that the ligand is more interacting with that of T2. So, T2 will be now higher in energy than that of E, the reverse of the octahedral complexes, right? So, here you can see that G will not be implying here. So, this one is T2 and this one will be becoming E, right? So, T2 will be higher in energy, E will be lower in energy, and the crystal field splitting here will be donated by delta T. T stands for what? Tetrahedral, right? Now, this is energy difference is 3 by 5 delta T. Again, it is reversed, and this energy difference will be 2 by 5 delta T. Okay. Now, this is a very important thing that delta T is much smaller than that of delta O. That means the tetrahedral crystal field splitting is much lower than that of the octahedral crystal field splitting. The relation between the two is that delta D equals to 4 by 9 delta O. Right. Now, a basic reason for this is that in tetrahedral complexes you are having only 4 ligands, right? So, the splitting will be less. While in octahedral complexes you are having 6 ligands, therefore the splitting will be large. This is one of the reasons that why tetrahedral complexes are having a lower crystal field splitting than that of the octahedral complexes, right? Now, also one thing you have to remember that tetrahedral complexes generally they always form high spin complexes. That means pairing does not take place in tetrahedral complexes because delta T is small, right? So, what happens here is that delta of the pairing energy in and rest we will complete it in the next class, right? We will practice some questions for crystal field theory, and the next concept that is left is the isomerism part. Isomerism is left, some part of crystal field theory. Basically, the theory has been discussed fully. We need to practice some complexes. Isomerism is there and carbonyl complex is there. carbonyl complexes we have to study, right? So 2 to 3 topics I guess are left now. So practice questions from BBT theory. It is very important from the examination point of view. That's all for today. We will meet in the next class. Happy learning to all.